Hello everyone, welcome back to another lecture of Chemical Process Design and Simulations course code CHE 446. And we know there are four CLOs of this course: Fundamentals, Simulation, Analysis and Related to Design. So our this activity is basically linked on heat exchanger network design and algorithm for splitting above and below pitch. We will refresh it, then trade-off in choosing the value of minimum value, steps of heat exchanger network design. Then we will solve one example and we will see how this system can be represented in Espen Energy Analyzer. Obviously, after these manual calculations, we will move to the Espen Energy Analyzer. So just for a recap, when a stream is above pinch, first we need to check that number of hot streams should be less than equal to number of cold stream. If they are not, obviously we need to split a cold stream. And then we need to check that Cp of hot should be less than equal to Cp of C, and then we place matches. If this is not true, then we split a hot stream, and opposite in case of below pinch. And we have studied the trade-off in choosing the value of delta T minimum, that for this particular range we can select the delta T minimum because it is representing the total cost which is minimum in this region. However, either moving to this side or moving to this side, the total cost will increase. And we have discussed this in detail in our previous lecture. And these were the design steps, that first we need to divide the problem at pinch. We have to divide the whole system above pinch and below pinch. Then we have to start design. We have to make sure that these conditions are met, and then we have to make sure that there is maximum heat recovery between process to process, and apply unavoidable or minimum possible external heating and cooling utility, and heating above pinch and cooling below pinch. So this is the example number 3, which we have discussed in our lecture number 25, and we had calculated cooling utility, heating utility and pinch temperatures. So the cold stream entering 20 degrees centigrade, exiting 125, Cp value is 2, hot utility 170, 63, cold utility 80 to 144 Cp value, and hot utility 150 to 30 degrees centigrade, 1.5 Cp value, and we will solve the system for a delta T minimum value of 10 degrees centigrade. And obviously this, the final temperature minus inlet initial multiplied by Cp, gives us the value of delta H, the heat load in kilowatt, obviously because the Cp unit is in kilowatt. If it would be in megawatt, we would have calculated it in megawatt. And these were the answers which we had calculated for a delta T minimum value of 10 degrees centigrade. Please be noted that for a delta T minimum other than 10 degrees centigrade, these answers would be different. So the pinch temperature is 85 degrees centigrade, hot pinch temperature 90, cold pinch temperature 80. Remember these two: hot utility 20 kilowatt and cold utility 60 kilowatt. So we have to obey all the three golden rules, that we cannot supply heat across the pinch, we cannot use cooling utility above pinch, and we cannot use heating duty below pinch. So first, as you know, we have to place hot streams, and then we have to place the cold stream. So 170 to 60 degrees centigrade, number 2, then from 150 to 30 degrees centigrade, number 4 stream. These two are the hot streams of the system. Then number 1, 20 to 135 degrees centigrade, and then number 3, 80 to 140 degrees centigrade. And we know the hot pinch temperature is 90 degrees centigrade and the cold pinch temperature is 80 degrees centigrade. So obviously our first task is to divide the system at pinch, and hot pinch temperature is 90 degrees centigrade. It means that above pinch it is 170 to 90, and below pinch it's 90 to 60 degrees centigrade. Similarly, this stream 150 to 90 degrees centigrade above pinch and 90 degrees centigrade to 30 degrees centigrade below pinch. Now the cold pinch temperature is 80 degrees centigrade. It means 20 degrees centigrade to 80 degrees centigrade below pinch, and above pinch 80 to 135. And this stream number 3, it is completely above pinch, that it is starting from 80 degrees centigrade and the pinch is at 80 degrees centigrade. So this complete stream will go above. If the cold pinch temperature would be like 85, then 80 to 85 would be below pinch and it would be above pinch. So now we will first check our first rule. What was the first rule? That above pinch, number of hot streams should be either less than or equal to number of cold stream. There are 2 hot stream above pinch, 2 cold stream above pinch. So the rule is satisfied. First rule is satisfied. Then below pinch, number of hot streams should be greater than or equal to number of cold streams. So there are two cold stream below pinch and one cold stream. So the rule is satisfied. Now, before starting the heat exchanger network design, you have to remember this point, and this is the crucial and important point, that the value of Dt at both ends should be positive. Like this is the hot stream which is going from 170 degrees centigrade to 90 degrees centigrade. And this is the cold stream which is going from 80 degrees centigrade to 140 degrees centigrade, and these two streams are exchanging heat with each other. Now at this end, which represents the hot in minus cold out, its answer should be positive. In this case, it is positive. 170 minus 140 is equal to 30 degrees centigrade. Similarly, hot out minus cold in, it should be positive as well. 90 minus 80 is equal to 10 degrees centigrade. If for some reason, like it is 100, then it will be 90 minus 100 means minus 10. So you cannot place these matches over here. You have to remember this, and we will continuously study this in today's activity, that we will check that at each point our dt is positive. If for some reason our dt is negative, we cannot place that match. We have to look for other alternatives. So in addition to the other rules, this rule should not be violated as well. As you can see, this is the system which is above pinch. Number of hot streams is equal to number of cold stream. Rule is satisfied. This is the hot pinch, 170 to 90 degrees centigrade. Cp value is 3. 90 minus 170 is minus 80. Multiplied by 3 is minus 240. Similarly, 150 to 90 degrees centigrade. 90 minus 150 minus 60. Multiplied by 1.5 minus 90 kilowatt. This is 80 to 135 degrees centigrade. So 135 minus 80 multiplied by 2, 110. And similarly, 80 to 140 degrees centigrade. 140 minus 80 multiplied by 4 is 240 kilowatt. Now, we can see this 240 kilowatt of hot and this 240 kilowatt of cold. These can be exchanged if we place a exchanger between 2 and 3. These two streams heat duty can be completely satisfied. But first we need to check whether we can match these without splitting or not. If you look at this first stream, which is number 2, you can see its Cp is 3. It cannot be matched with this one, because its Cp value is higher. Cp of H is higher is Cp of C. If we have to match these two, then we need to split this string. Then 3 can be matched with 4, because Cp of H is less than Cp of C. Similarly, this 1.5, this can be matched with 1 and 3 because it's 1.5, the value is 2 and the value is 4. So there is only one problem which we can see, that this number 2 stream cannot be matched with number 1 stream. But we can see that the 240 kilowatt which this stream is giving, this stream can completely take. So first thing is to install an exchanger between these two streams, and obviously we need to check whether our all rules are satisfied or not. So for exchanger number 1, Cp of stream number 2 is 3 kilowatt per Kelvin. Cp of stream number 3 is 4 kilowatt per Kelvin. Rule is satisfied. Cp of H is less than equal to Cp of C. And the inlet temperature was 170 degrees centigrade. The outlet temperature of hot stream was 90 degrees centigrade. Multiplied by Cp, the inlet temperature of cold stream was 80 degrees centigrade. The outlet temperature was 140 degrees. All the heat is transferred between these two streams. And if we see, the entering temperature is 170 degrees centigrade. The exit temperature is 90 degrees centigrade. Similarly, here the entering temperature is 80. The outlet temperature is 140. So 170 minus 140, 130. Satisfied. dt is positive. 90 minus 80, 10. dt is satisfied, positive. So these two streams are no longer available for heat exchange, 2 and 3. It means what we have left with 4 and 1. And obviously these two can be matched, because without the stream splitting, because the Cp of H is less than Cp of C. It can exchange a maximum of 90 kilowatt while it requires 110 kilowatt. Means for the 20 kilowatt we require here the heating duty. So the second heat exchanger will be placed between these two streams. Now we will check what is the outlet temperature over here. Remember, this is 150 to 90 degrees centigrade. It will completely exchange heat, but it is from 80 to what temperature? We have to compute that temperature in the system. So for heat exchanger number 2, Cp of stream number 4 is 1.5 kilowatt per Kelvin. Stream number 1 is 2 kilowatt per Kelvin. Rule is satisfied. Now from 150 to 90 degrees centigrade. As I have told you that hot stream will completely exchange its heat multiplied by 1.5 Cp value. Now this is X. We do not know the final temperature of this cold stream minus inlet temperature, which is 80 multiplied by 2. So once we compute it, its answer is 125 degrees centigrade. And once we draw this exchanger diagram, it is from 150 to 90 degrees centigrade. It is from 80 to 125 degrees centigrade. So this end, it is plus 25. This end is plus 10. So it is okay. This exchanger can be placed. So it means here the temperature will be 125 degrees centigrade. So now 135 minus 125, it will be 10 multiplied by 2, it will be 20 kilowatt. So for 20 kilowatt, we require a hot utility. And if you can see that 240 is completely exchanged with 240, and it then 110 minus 90. So it means 20 kilowatt was required for this. So the answer here is 20 kilowatt. And if I take you back, the hot utility which we computed from the problem table or the graphical method was 20 kilowatt. So it means we have done the right connections of heat exchangers, because the value calculated from the problem table approach is the same value which we are getting from the design. So above pitch design is completed. So we have installed 3 exchangers. 2 were related to the process to process heat stream recovery, and 1 was related to the utility. Now we will move to the below pinch system. So this is the representation of the system below pinch. The hot pinch temperature is 90, cold pinch temperature is 80. This is stream number 2, this is stream number 4, this is stream number 1. The stream number 3 is completely utilized above pinch. So it cannot exist below pinch. Now this is from 90 to 60 degrees centigrade. Cp value is 3. The difference multiplied by 3 is 90 kilowatt. Similarly, it is at 90 degrees centigrade to 30 degrees centigrade, 60 degrees centigrade are total temperature difference. Multiplied by 1.5, 90 kilowatt. This is 20 to 80. So difference is 60 multiplied by 2, 120 kilowatt. Now we can see that this number 2, which is the number 2 stream, can be easily matched with number 1 stream because the Cp of H is higher than Cp of C. However, there is a problem with stream number 4, that we need to do splitting of this cold stream if we need to proceed. However, there is some flexible margin over here where we can proceed without splitting. So what we need to do for exchanger number 3, Cp of stream number 4 is 1.5 kilowatt per Kelvin. Cp of stream number 1 is 2 kilowatt per Kelvin. The rule is not satisfied. However, we can proceed. How we can proceed? Since H in minus C out and H out minus C in is equal to the value of delta T minimum. What was delta T minimum in the case? 10 degrees centigrade. We will make a connection between these and we will see that if H in minus C out and H out minus C in, if this value is equal to delta T minimum, we can proceed without stream splitting. This rule is only applicable for below pinch system. And for such systems, exchanger connection should be from away the pinch. How I will tell you now. So we can proceed on this assumption. Hot stream 90 degrees centigrade to 30 degrees centigrade. Obviously, it will completely exchange its heat because its requirement was 90 kilowatt. Multiplied by 1.5, x minus 20 multiplied by 2. So this x value is 65 degrees centigrade. Now, if you see, it is from 90 to 30 degrees centigrade. It is from 20 to 65 degrees centigrade. So this temperature difference is 25 degrees centigrade, greater than delta T minimum. This difference is 10 degrees centigrade, equal to delta T minimum. Since it is equal to the delta T minimum, in this case it is higher than delta T minimum, in this case it is equal to delta T minimum. So we can proceed below pinch without doing a stream splitting, but please be noted that this rule is only applicable for below pinch system. So you can see we have placed a match between the stream number 4 and stream number 1. Its requirement was to give away 90 kilowatt while it could take 120 kilowatt. So it means that it still can take 30 kilowatt of heat. And from where it will take from this stream number 2. Now, what I was telling, that away from the pinch, this is the pinch region. Once you are doing such connection, it should be away from the pinch. Like when we install a new exchanger, it will be like here. So this exchanger installment is adjacent to the pinch, but this is away from the pinch. So you have to keep that rule in mind. Once you are doing this connection below pinch, once you are violating some rule of CP, that for violating the rule which is CP of H is not higher than CP of C, you can design or place match away from the pinch. This is away from the pinch. If you place here, then that's not true. So first thing, in upcoming cases we will also see it, and obviously we will see an activity where we will do the splitting part, but obviously this is the first rigorous activity, so we are not going for the splitting. And in the second case, it will go from 65 to 80 degrees centigrade, and we have to compute the temperature from where 90 to further temperature, so it's 80 degrees centigrade. But how it is calculated, let me take you to the calculation. And you can see it requires only 30 kilowatt, it can exchange 90 kilowatt, so it means minus 90 plus 30, so minus 60 kilowatt heat duty it will still be available for heat exchange, but there is no process stream available, so it will be exchanged with the utility. So for exchanger number 4, I have labeled it as exchanger number 4 in terms of the process to process recovery, otherwise it is exchanger number 5. You have to keep that in mind. So CP of stream number 2, 3, stream number 1, 2, rule is satisfied. 90 minus X. Obviously, you do not know the final outlet temperature of hot stream, but you know that cold stream will completely exchange its heat. So the answer is 80 degrees centigrade. Now you can see 90 to 80 degrees centigrade. It is 65 to 80 degrees centigrade. Here the temperature difference is 10. Here the temperature difference is 15. Both answers are in plus. So you can place this match over here. So this is 80 degrees centigrade. Now from 80 to 60, the temperature difference is 20 multiplied by 3. So it means for remaining 60 kilowatt, you require a cooling utility of 60 kilowatt. And this cold utility is same as you have calculated in the problem table approach. As you can see here that the cold utility requirement was 60 kilowatt, hot utility requirement was 20 kilowatt. Now we will draw a final diagram of this whole connection of the system. So as you can see, this is the overall schematic of heat exchanger network design. This is exchanger number 1 between the stream 2 and 3, exchanger number 2 between stream 4 and 1 above pinch, and this is the hot utilities. Requirement means the utility exchanger. Similarly, this is away from the pinch. So this is away from the pinch, E3, E4. So there are 4 exchangers of process to process, and there are 2 exchangers which are using the utility. So there are a total of 6 heat exchangers installed within this system. And if you remember for our system that how we had calculated the total number of units, U minimum is equal to N minimum minus 1, and N minimum is how many streams are there? There are 6 streams. 1, 2, 3, 4 plus 2 utility. So 6 streams, 6 minus 1 is equal to 5. So there are a minimum of 5 units, and here there are 6 units installed. But there is one more definition involved in it, that is streams minus 1 above pinch plus stream minus 1 below pinch. So there are 4 streams plus this one. There are 5 streams minus 1. So it is 4. How many streams are there? 4 streams minus 1 means 3. अब अगर आप इसको देखें तो U minimum is equal to number of streams minus 1 above pinch. Number of streams 5 minus 1 4. Number of streams 4. 4 minus 1 3. So 4 plus 3 7. How many exchangers we have installed? 6. So it means we have still saved one exchanger in this system. This is the new definition of calculating the minimum number of units. One definition was related to the whole system, that we required 5 exchangers for the system. But when we have divided the system into the pinch, and we have divided the system above pinch and below pinch, then we have to take it like above pinch n minus 1, below pinch n minus 1, and then summing these, and that will be your U minimum. And this is the representation in the Espen energy analyzer. As you can see, this is of 240 kilowatt, this is 90 kilowatt, this is 30, this is 90. The cold utility requirement is 60 kilowatt, the hot utility requirement is 20 kilowatt. So once we move to the Espen energy analyzer, we will see how we can achieve this systematic diagram and how we can prepare this. So that's it from this lecture. Thank you so much.